Hello everyone. Kotongwane, the native god here. On this video, we are going to look at a topic based on beams. Right now, for engineering science N3, beams is under moments, right? And moments essentially fall under statics. That's the topic where we look at conditions of equilibrium, right? So we are going to, have a look at this question. It's based on beams, so that we know how to, or we know our way around calculations based on beams, how to calculate reactions, the different types of loads that you can expect on a beam, how you treat those loads, or how you use those loads when having to apply conditions of equilibrium, right? And how you draw a shear force diagram, right? Now 2.1, they want us to define the term uniformly distributed load, right? Uniformly distributed load is also known as a UDL, right? UDL stands for uniformly distributed loads, right? So I've written here. So for 2.1, UDL refers to a load that is spread evenly either along the entire span of the beam or along a certain portion of the beam. Right, so you will see exactly what I'm referring to when we discuss 2.3. Right, so you get different types of loads for beams, right? Or for native engineering, the loads that we look at, or for engineering science N3 and N4, the two types of loads that we look at is the point load as well as the uniformly distributed load, right? And I'll explain how you deal with the UDL if you have one on the exercise that you are looking at, right? 2.2, state the law of moments, right? The law of moments is based, or is one of the conditions of equilibrium. Now, if you are doing moments, it means you've already done the first module. If you're doing engineering science N3, it means you've already done the first module, which is motion. Motion, energy, and power, right? In doing that module, we looked at a topic based on dynamics, where we consider Newton's laws of motion, so the first, second, and the third law. And as you should know, the third law, right, is essentially based on conditions of equilibrium. Right, conditions of equilibrium, we get 2 of them. Right, one is static equilibrium, the other one is dynamic equilibrium. Now, static equilibrium, right, as the term static suggests, right, that is when you have a system of forces that are essentially cancelling each other out, and essentially the object you are looking at is stationary or is not moving, right? So when the object is not moving, right, and is not crumbling or hasn't crumbled, it means the system of forces acting on that object, right, are cancelling each other out, hence the resultant force is 0, or F net is 0. Then you get dynamic equilibrium, where the object you're looking at is in motion, right, but said object is not accelerating. So if the object is in motion but it's not accelerating, then we take it as being in dynamic equilibrium. Why? Because remember that F net is equal to ma. So if this is 0, it means that is 0, right? So as long as F net is 0, it means the system of forces acting on the object are essentially cancelling each other out, hence the system is in equilibrium, right? So law of moments, right, is one of the conditions of equilibrium, and it states essentially that when you have a system in equilibrium, right, the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about that same point. Right? That is, in a nutshell, how you state the law of moments, or what the law of moments is. Right? You are also able to state this mathematically. Right? Mathematically, you can say, for instance, the sum of clockwise moments is equal to the sum of anti-clockwise moments about the same point. So the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. Right, so that is how you express it mathematically. Right. Right, now let's look at 2.3, and it reads as follows. A beam is 6 meters long and supported 1 meter from the left end and 2 meters from the right end of the beam. So we have a beam, it's 6 meters long, it's supported 1 meter from the left end, right, and 2 meters from the right end, right. So we have a beam, it's 6 meters, it has a support, right, 1 meter from the left end, which is this one, and the other one is 2 meters from the right end, which is that one, right. And they say there is a uniformly 12,243 kilograms per meter placed between the two supports, right. So here they were supposed to say there is a uniformly distributed load, right, placed between the two supports, right. So you have a support here, you have a support here. Between the supports is a UDL, and the magnitude of that UDL is 12,243 kilograms per meter, right. And then they say a point load of 300 newtons is placed on both ends of the beam, right. Both ends of the beam. At one end you have a 300 newton point load, at this end you have another 300 newtons point load, and a 200 newtons load is placed 1 meter from the right end of the beam, right. So from the right end 1 meters in, you have this 200 newtons point load, right. Now, as far as the questions, they said 2.3.1, calculate the reactions of the two supports, right. Now, obviously, first thing, you need to draw the beam, right. Even if the beam has been given to you, right, or has been drawn for you, I always advise students to always redraw the beam, right. The reason for that is so that just in case you have to work out the span of the beam, or the distances of the beam, maybe not the distances of the beam, but the distances in terms of the critical points. Now, the critical points on the beam are the points where you have point loads, where you have the reaction, the beginning and end of the beam, as well as the beginning and end of a UDL, right. If you have a UDL, more especially, it is important that you redraw the beam so that you'll be able to rework out the distances in terms of having to resolve the UDL into its weight component, right. Now, the UDL, for instance, this one is in kilograms per meter, right. Normally, the UDL is expressed as Newton per meter, right. Now, obviously, if you look at this magnitude, right, if you look at how the UDL is expressed currently, we cannot use it as it is in having to apply conditions of equilibrium. Remember, conditions of equilibrium, if you're using moments, right, moments is force times distance. A force is in newtons, not Newton meters, so we cannot use this because this is in Newton per meter, right. Also, if you're using, say, sum of forces going up is equal to the sum of forces going down, or if you're using the sum of forces along the y-axis is equal to 0, right? You cannot use this magnitude as it is. Why? Because with either of these, right, we use forces, and forces are in newtons, right? So that is to say that when you have a UDL, however it is expressed, you must resolve it into its weight component, right? So remember, the weight of anything always acts at the center of its span, right? So we are going to resolve, or you always have to resolve this into its weight component. The weight component would be in newtons, hence you can use that in applying conditions of equilibrium, right? So by that I mean we have a UDL, right? It's in kilograms per meter, right? Even looking at this intuitively, right? You can tell that in order for this to be in newtons, right, you obviously have to change this into newtons, right? So remember, if you have a mass, right, the weight of the object would be its mass times the gravitational acceleration, right? So similarly with this one, right, to change this into newtons, right, or to convert this into its weight component, you have to multiply this by g, right? And then to change this, right, to convert this into into a newton component, right, or to express this in terms of newtons, right, you have to multiply this by g, and then to convert this into its weight component, right, meaningly to get rid of this m, which is in meters, you have to multiply this, right, by the span of the beam. So by that I mean, so we want to express this, or want to convert this into its weight component. We look at how it is expressed. It is in kilograms per meter. So meaning that its weight component will be 12,243. Remember, this is in kilograms per meter. Right, we want to convert this to its weight component. So you multiply this by g. G is 9,8 for engineering science, right? But multiplying this by g, right, only converts the numerator into newtons, right? Then to get rid of this, you then multiply it by the span of the UDL, right? Now, as far as the span of the UDL, remember that the entire beam is 6 meters, and we are told that this reaction is 1 meters from the left. This one is 2 meters from the left. So 6 minus 2 minus 1 is essentially 3, meaning that if the UDL is between the two supports, it means it is 3 meters long. Then you multiply this by 3. Hence, this and that cancel, right? And multiplying the mass by g gives us the weight, and this will be equal to so if you punch this in your calculators, you should get 359,944 newtons, right, which is essentially, right, so now this has been converted into its weight component. Now you will be able to use this in applying conditions of equilibrium. Why? Because now this is expressed in newtons, right? And like I said, the weight of anything always acts at the center of its span, right? So we have 359,944 newtons, all right? And then the weight component is going to act at half of this span. Half of 3 meters is 1,5. So this here is going to act 1,5 from the left and 1,5 from the right hand side. Right, that is what I mean by the weight component acts at the half of the UDL's span. right? So now in calculating the reactions, or in applying conditions of equilibrium, we are not going to make use of this. Instead, we are going to make use of its weight component. All right. Right. Now let's look at 2.3.1, calculate the reactions of the two supports. Right. Now we'll be able to calculate the reactions at the two supports. Why? Because we have all of the forces, or all of the loads that are on the beam, right, are expressed in terms of newtons, right? Hence we'll be able to apply conditions of equilibrium. So applying conditions of equilibrium, we first take moments about point C, right, thus eliminating this reaction, so that we'll be able to get the magnitude of this reaction. Right, so we say take moments about C, right? So we are taking moments about C, right, so that we are able to calculate the reaction at point B. Right, so this is 2.3.1. Right, so we are taking moments about point C, so that we are able to calculate the reaction at point B, right? Now when you take moments about point C, now we are going to apply conditions of equilibrium, right, using the law of moments. Sum of clockwise moments is equal to the sum of anti-clockwise moments, right? Now we are going to look at the turning effect that each of these loads has towards the point we are taking moments about, right? For instance, we're going to look at this 300 newtons point load, right? You look at the turning effect it is going to have towards point C, right? It is headed downward, so the turning effect will be like this, right? So looking at this kind of turning moment effect, would you say this is clockwise or anti-clockwise? Obviously this is going against the clock. So when taking moments about C, right, this load in particular has an anti-clockwise, right? It's an anti-clockwise turning effect. Then you look at your reaction at B, right? This one is headed upward, so the turning effect would look like this one here, right? Obviously this has a clockwise turning effect, so this one will be clockwise. Now we look at the weight component of the UDL heading downward. This one will be anti-clockwise, so anti-clockwise, right? Then you look at the 200. This one will be, it's heading downward, so the turning effect will go like this, which is going with the clock. So this one is clockwise. The 300 newtons, right, on the right hand end of the beam will also have a clockwise turning effect, right? So as far as clockwise moments or forces that have a clockwise turning effect towards point C, right, we have the reaction at B. So that will be the reaction at B times, remember a moment is force times distance, right? Here is the force, the distance is the distance from that force to where we are taking moments about. So what is the distance between point B and point C? It is 3 meters. So this times 3, right, plus, right, the next force going clockwise is the 200. So this will be 200 times the distance between 200 and point C, that's 1 meter. So this will be 1 plus the 300. Right, remember the 300 is also having a clockwise turning effect. So 300 times this distance, which is 2 meters. So times 2 is equal to, now we look at the anti-clockwise, or the forces that have an anti-clockwise turning effect. Right, first you have the 300, right? From here, right, 2 point C is 3 plus 1, so that's 4. So here you have 300 times 4 plus, right, the weight component of the UDL, right? Remember, it also has an anti-clockwise turning effect, right? So the 359,944, right, times this distance, which is 1,5, right? Now this is why I say you need to redraw your beam, so you can work out or rework out the distances from the forces, right, from the weight component. Because remember, initially this distance was 300, but because we have resolved this into its weight component, it is important that you know the distance, or yes, know the distance from where this force is acting, right, to either of the supports, right? Hence here, instead of having 3 meters, now you have 1,5 and 1,5, right? So you have the 359,944 times the distance between that force and where we are taking moments about, which is that 1,5. So here you have 1,5, right? Then of course here you have only one unknown. We are looking for B, so here we say 3B is equal to, and then you take both of these terms that side. When you do that, we will be left with, so this remains positive, right? And then obviously when you transpose these two, they then become negative. So minus this, that is negative as well, right? And then because we're looking for the reaction at B, you then get rid of, or you make certain that the coefficient of B is 1 by dividing by 3. Then of course what you do on the left, you do on the right, so divide by 3 here as well, and this gives us the reaction at B. So if you punch this in your calculators, you should get 313,305 newtons. That is our reaction at B, right? So now we are going to calculate the reaction at A by taking moments about B. So we eliminate B by taking moments about it. That way the reaction at C will be our only unknown. All right, so remember that now. We no longer have this. Right. So now we are going to take moments about, what is this? I'm supposed to say take moments about B now, right? We are now taking moments about B, so we can get the reaction at C, right? Sum of clockwise moments is equal to the sum of anti-clockwise moments, right? We are now taking moments about B. Hence now we are going to look at the turning effects that each of these loads has towards B. Right, looking at the 300, right, looking at the 300 Newton force, right, this one is or has this turning effect towards B, that's anti-clockwise. So this one is anti-clockwise, right? You look at this weight component, it is having an a clockwise turning effect, Right, this one also has a clockwise turning effect. This one also has a clockwise turning effect. So clockwise, that's clockwise as well. Right, the reaction at C has an anti-clockwise. It's going against the clock, so this one is anti-clockwise. Right. So two of these loads, this one and this one, are having an anti-clockwise turning effect towards point B, and then the weight components, the 200 and 300 point loads, all have a clockwise turning effect towards point B. Right, so we have, what is this, the 359,944 times the distance between this weight component of the UDL and where we're taking moments, that's 1,5. So that's 1,5 plus you have the 200 newtons point load. The distance between this and point B is 3 plus 1, that's 4. So times 4 plus the 300 times the distance between this 300 and this point, right, point B. So that's 3 plus 2, which is 5. So times 5 is equal to anti-clockwise, or the forces that have an anti-clockwise turning effect. That's this 300, that's 300 times 1. So here we have 300 times 1 plus reaction at C times the distance between C and where we are taking moments, that's 3 meters. So times 3. Right, and then here we only have one unknown, which is what we're looking for. So to get that unknown, it means we'll have 3C is equal to, then we are going to transpose this term to that side, which means we will have this, right, minus, and then this, when you transpose this to the other side, it will be negative. And then to get C, you simply divide both sides by 3, thus getting rid of that, so that we are only left with the unknown. Now if you punch this in your calculators, you should get 846,639 newtons. Right, and that is how you would calculate the reactions. Right, after having calculated the reactions, right, to prove somehow that your beam is in static equilibrium, right, you then have to calculate the sum of forces along the y-axis, and they must be equal to 0. Right, by that I mean, you say sum of forces along the y-axis is equal to 0. Right, this here is a condition of equilibrium. Right, so that is to say that if you add the forces that are parallel to the y-axis, they must be equal to 0. If they are, right, it's more than likely that the reactions you calculated or the magnitude thereof is correct. Right, either way though, this is the best way of checking if your beam is indeed in static equilibrium. Right, this will allude to whether or not the reactions you calculated are correct or not. So now we add forces, right, looking at if the forces are going up or down. Remember that forces going up, you take them as positive. Forces that are going down, you take them as negative. Right, so both reactions, so B being 313,305 right, plus reaction at C, which is 846,639. Both are positive because they're heading upward, right? And then you have the two 300 Newton point loads. So minus 300, minus 300. You have the 200 Newton force point load, so minus 200. And then we have the weight component. The weight component of the UDL, which is 359,944. Now if you sum this up, you will indeed get 0 newtons. Right, that is how you calculate reactions. Right, now let's look at 2.3.2. Draw a shear force diagram showing all main values. Right, now this one is going to be very important as well, so pay attention, so that you know exactly how to draw, or at least you get familiar with how, or the guidelines of how to draw a shear force diagram. Right, now in drawing the shear force diagram, this is 2.3.2. in drawing the shear force diagram, what I like to do is to redraw the beam, right, and use it as a reference in drawing your shear force diagram. Right, in drawing your shear force diagram, right, so what you will do is you are going to draw lines, right? So from having critical points, if you remember earlier, I spoke of critical points on the beam, right? And I said that those critical points are the beginning and end of the beam, right? Where you have point loads, where you have reactions, the beginning and end of a UDL, right? This one is not so important, right? We don't necessarily take it as a critical point on the beam, right? That is where the weight component of the beam is acting, right? We don't necessarily take it as a critical point, right? Now here, remember that we weren't given the schematic illustration of this beam, right? We had to draw it ourselves, hence we had to name the critical points on our own, right? And where I've given a label for a point, right, is a critical point. So this is where the beam begins, hence it's a critical point. Also you have a point load, right, hence this is a critical point. Here you have a reaction, so it's a critical point also. This is the beginning of a UDL, making this a critical point. This is the end of a UDL, making it a critical point. Aside from that, you also have a reaction, making this a critical point. You have a point load here, making this point a critical point. This is the end of the beam, making it a critical point. Also, you have a point load at this point, making it a critical point. All right. So the points that I've labeled here are all critical points on the beam. So in drawing your shear force diagram, you are going to extend vertical lines from all of the critical points. So from that I mean, so you want to have a line extending from here right, you're going to have a line extending vertically from all critical points. right? And I have one here, have one here, have one there, and there. Right now, I've extended I've extended vertical lines from all of our critical points. Right. The next thing you do is, now this you can draw as a faint line, right? But what you do is you draw somewhat of a sectioning line on the right hand side of each of the critical points, right? For instance, I'd have, say, that line. Let's change the style, right? So draw a sectioning line on the right hand side of each of the critical points. Right, you draw a line on the right hand side of each of the critical points. Right, pay attention to these guidelines. Right, so you draw a line on the right hand side of each of the critical points, and then on the points where you have a UDL on the immediate left of the beam, right, on the immediate left of that point, right, you must then draw another sectional line there. By that I mean, you look at your critical points, then you look at if you have a UDL on the immediate left. If there's no UDL on the immediate left, you leave the one sectioning line that you've drawn on the right hand side, right? So you do the same thing here. There's no UDL here, so you leave it as it is. Now at this point, there is a UDL on the immediate left. So because there's a UDL on the immediate left, you then draw another line, right, on the left hand side of the point. Right, there's no UDL on the immediate left here, so you leave it as it is. Same with this one. Right, this comes in handy when having to show the shear forces, right, that are on each of the critical points. Right, now in drawing your shear force diagram, you must have a zero line. Right, say we take this here as our zero line, so this will be 0 newtons. That's 0 newtons. So it means this is where our shear force diagram is going to begin. Right, our shear force diagram begins at 0. It must end at 0, thus indicating that our beam is indeed in equilibrium. Right, so what you're going to do is, on your calculators, right, starting with this point A, right, we are now going to consider forces on the left of this section. Right, you are going to consider forces on the left of this section. Right, in having to draw the shear force diagram, right, or in having to calculate your shear forces, you are going to consider forces on the left of each of the section. For instance, on this section, point A, we are now going to consider forces on the left. Forces on the left is this 300 newtons. It is headed downward, which means, seeing that it is headed downward, it means from 0, right, from 0, this is what we have. So we have the negative 300 newtons, right? So those are our shear forces at point A, right? So on your calculator, this is what you must have, right? It's the negative 300. right? Because as we move from point A to the next point, right, the forces we add or the forces we subtract, we are going to add or subtract from the negative 300. Right, so in this case it's the negative 300, but in other cases it could be something different. So it could be something positive, whatever the case. Right, it is important that you write down your first shear force, and the first shear force here is negative 300. Right, now we move on to the next point. The next critical point is point B. Now we are going to consider forces between the section at B and the last section. Right, we are going to consider forces between this section and the last section. Right, bearing in mind that our reference is the negative 300. Right, so you're going to say negative 300, and then the forces we add or subtract depending on which forces we have between the current section and the last section. In this case, that force is this reaction at B. Right, so remember the reaction at B, right, was that 313. So here you have 313, 305 newtons, and then the reaction at C was 846, 639 newtons. Right, so we have between the current section at point B and the last section, we only have one force to consider, that's this reaction, and it is headed upward. So bear in mind that your reference is negative 300, so you say negative 300. Seeing that this is heading upward, you say plus the 313, 305. Right, and you should get 13,305, which is positive. Now what you do here is, in having to draw this part of the shear force diagram, right, you look at if we have a UDL between point A and point B. There is no UDL between point A and point B, and the way we show that on the shear force diagram is you draw a line going straight across. Right, this is showing that between these 2 points there is no UDL. Right, and then the number we got, or the magnitude we got, is positive. Then you draw a line, right, a positive line. Here we have the 13,305 newtons. Right, this is what we have. Right, then we are done with the shear forces at this section or at this critical point. Now we move on to the next point. Right, moving on to the next section. Right, remember here we have two sections, so we are first going to consider forces between this section and the last section. Right, in doing so, bearing in mind that our reference is now 13,305, so this is what you must have in your calculators. Right, now considering forces between the current section and the last section. Right, the only forces to consider are the ones based on this UDL. Right, now we are going to consider the entire span of the UDL. Hence, when resolving this UDL into its weight component, right, we are going to use exactly this, because we already know that if you resolve this into its weight component, this is what we get. Right, the 359,944. Right, it is a weight component, hence it is acting downward, hence you take it as negative. Right, so what you do here is you say this, and then because this is acting downward, you say minus the 359,944. Right, and we should get negative 346,639 newtons. Right, Now, between A and B, we have a UDL, and the way we show that on the shear force diagram is by drawing a line that is diagonal, right, to that point. Right. Then move on to the next section. We have two sections. Remember, at this point, we are done considering forces on the left of this section. Now we are going to consider forces between this section and the last section. And the only force to consider is the one of this reaction. As the reaction is positive, therefore we are going to say negative 346,639, and you're going to add the 846,639, and you should get positive 500. Right, so then from here you then go straight up, right, to positive 500. So this is positive 500 newtons. Right. After getting this, it means now we are done with shear forces, right, at this critical point. Now we move on to the next critical point. Remember, here there is no UDL. Because there's no UDL, it means you have to go straight across or draw a line going straight across, right? And then we consider forces on the left of this section, right? Consider forces between the current section and the last section. So forces between these two sections, which is this negative 200. So we now say the positive 500 minus the 200, you should get 300. Right, so this is 300 newtons. Right, and then again, because now we are done with this, we then move on to the next critical point. Right, there is no UDL between these 2 points. Therefore, you draw a line going straight across, and then consider forces between this section and the last section, which is the negative 300. It's negative because it's heading downward. You then say the positive 300 minus the 300, which gives us 0, which brings our shear force diagram back to 0. Right, and this becomes your shear force diagram. Right, this here then becomes your shear force diagram. Right, or it should more or less look like this. Right, and that is how you draw a shear force diagram. Now the shear force diagram is important because it shows us points where the beam is experiencing the most bending, and those points is where the shear force is equal to 0. So that is to say that points on the shear force diagram where the shear force diagram is equal to 0, those are the possible points where the beam is experiencing the most bending. So it could be this point, this point, this point. Right, so those 3 points. Right, either this one, or this one. Now for engineering science N3, we do not draw the bending moment diagram. Right, but it is important to note why a shear force diagram is important. Right, and one of those reasons is that it indicates to us where the beam is experiencing the most bending, and where the beam experiences the most bending from the perspective of a shear force diagram is where the shear force diagram is equal to 0. So it's equal to 0 here, equal to 0 here, equal to 0 there. So those are the possible points where the beam is experiencing the most bending. Right, so I hope you found this video helpful. Stay tuned for more content on engineering science. See you on the next one.